Hello, my name is Jim Plank, and this video is really number 3. We're zero indexed in the Neuromorphic Computing with TENNLab series. This is the first video walking you through the C++ workflow. We're going to do a walkthrough of that, plus two tools that are part of the workflow called the network tool and the processor tool. So the point of this video is multifold. We're going to have you clone and compile the C++ version of our software, and we will do that together. I'm going to show you a very simple spiking neural network that performs the XOR operation on the RISP neuroprocessor, and we're going to use that network kind of as the motivator throughout this video. Then we're going to introduce you to a program called the network tool, which lets you explore networks on our software framework and modify them, query them. And then there's another tool called the processor tool, where you'll be able to load a network onto a specific neuroprocessor and then apply spikes to it, run it, look at outputs, look at network state, etc. Basically, the goal is when you're done with this, you'll have some tools at your disposal to do very basic things with networks and processors. So we're going to switch here and go. I'm on a Macintosh running Bash. This should be working on pretty much any Unix-like system. And what we're going to do is we are going to go through and pull and compile the repo, make sure that you can do that. This is a play-along video, so the intent is that you should be doing these sequence of activities yourself on your own computer and pausing the video when necessary. So first off, here's the framework. It's a repository on Bitbucket on this URL. And let me also just show you documentation. There's a directory called Markdown, and if you go down to the bottom of Markdown, there is a file called walkthrough XOR RISP, and that contains everything that we're going to be doing in this video. So you can use that as a reference if you'd rather, instead of the video or in addition to the video. Okay, so let's go back to the main page of the repo and let's go ahead and clone it. And we are going to clone it afresh on our computer. So I keep all of my repos in the directory circ repos. Let me get rid of any framework that I have. And then we're going to go ahead and clone. And if this takes too long, I'm going to pause so that you don't have to wait for everything to work. Okay, that finished. Took about 30 seconds. Now, one unfortunate thing you need to do, let's go ahead and go into the framework directory. All right, you can see I'm in circ repos framework. One unfortunate thing is it doesn't put eons in, and even though we're not going to use eons in this talk, let's go ahead and get eons in the right place. So if you do an ls of eons and you see nothing, that's because there's just a placeholder for it. So go ahead and kill that and then grab it from Bitbucket. So here, search for eons. There's eons. And then we'll go ahead and clone eons. And we're going to clone it here in the as a subdirectory of the framework. This shouldn't take long at all. Okay, we're all good now. Okay, now we're going to do some compilation just to make sure that the framework is compiling correctly. Kill that. And so first thing we're going to do is we're going to make the network tool. So say make, this is in the main framework directory, make bin network tool. And this is going to take, it'll probably take 20 seconds so because it has to compile the framework. And that'll be the only time you'll compile the framework. So after that, the framework will be done. It's about 7 files. You can see it going on here. Right after spike encoding, it's probably done. Yep. And then we've got the network tool. And we're there. Okay, so now if you list the bin directory, you've got a program there called the network tool. We're going to do one more compilation step, and that is we're going to make the processor tool. Now, the processor tool is a C++ application, so it's in the directory CPP apps. So we move to that directory, and now the make file here, you always have to specify a processor and an application. So we're going to use the RISP processor. So equals RISP. And the application is going to be processor tool. Okay, and we would compile that. It's actually going to go through, compile the RISP simulator, which again, it'll only do that once. Then it'll compile the processor tool. Actually, it looks like it went in the other order. Now it's doing the RISP processor, and then it's going to link them together and create an executable file. Okay, and so if we list the bin directory here, you'll see there's an application called processor tool RISP. That's in this directory. The applications will always be application/processor. The processor code is compiled into that binary, unlike the Python workflow where all of them are compiled in, and then you can select them at runtime. With C++, you compile in your application and you compile in your processor. Okay, so if you've reached this point, now you are good to go. We are going to move back to PowerPoint and talk a little bit about some networks and some processors. So I'll do that now. We'll go from the current slide. Okay, in TENNLab, we've got 5 now neuroprocessors that compile and run within the framework. And I just have them listed here. So we have RISP, which is what I'll go over today, which is extremely simple integrate and fire processor. We have Ravens, and Ravens is part of our Air Force funded project where we're looking to build neuroprocessors with memristive components. And so that's Ravens. GNP is a software only project. Its goal is to give you the ability to build neuroprocessor with a lot of standard bells and whistles in it. So leak, refractory periods, plasticity, etc. Those are all built into GNP to allow for exploration and or extension if you want to extend some of its features into a different neuroprocessor. Caspian comes out of Oak Ridge. It's an all-digital project that has its own neuroprocessor model. And then we're working on the Izikovich model. I probably should have put it in parens, but we have the neuron model built. This is a interesting dynamic neuron model that comes from a paper in 2003 with very interesting dynamics in it. Now you'll notice I have these little Greek symbols color-coded. Red means these are done in simulation, which of course all of them are. And then they're differing levels of hardware implementation. So RISP has a microcontroller implementation, where the microcontroller actually reads spikes on its input pins and produces spikes on its output pins. A couple of these, Ravens and Caspian, have FPGA implementation with various types of inputs and outputs to them. And then also Ravens has been going through chip fabrication, several phases of it as part of our ongoing AFRL project. So I'll talk a little bit about the RISP neuroprocessor. This is the one that we're going to use in this walkthrough, largely because it's so simple. So the neurons are integrate and fire, simple addition. There's an integration cycle, meaning that we integrate over a unit time step, and then it is only at the end of the time step that we compare what the action potential of the neuron is with the threshold to decide whether or not to spike. And so that unit integration, what it really means is that synapses have effectively integer delays, because if a synapse fires in the middle of a cycle, it doesn't matter because it's the comparison doesn't happen until the end of the cycle. There is one parameter, which is should neurons leak or not? And if leak is set, they leak their entire charge at the end of every time cycle. So if they don't fire, they leak all of their charge. You can configure them not to leak, which means they will hold their charge values indefinitely until the charge accumulates enough so that it fires. There's no plasticity, etc. It's very simple. The simulator is really fast, and there's documentation about RISP there in those URLs. Okay, here's a network that we've developed with RISP, and this network performs an XOR operation. Now, it's a little busy on the picture, but basically we are performing the XOR of 2 values, A and B. Each of those corresponds to an input neuron. They're labeled A and B, and I also have the numbers so that the neurons are numbered 0 through 4 because there are 5 neurons. So the A neuron is numbered 0, and the B neuron is numbered 1, etc. There is an output neuron, that's neuron 4, which is denoted A, X, or B. And then there are two hidden neurons in the middle there, neurons 2 and 3. We have 6 synapses. Every synapse has a delay of 1 and a weight of either 1 or -1. The negative ones are in green. And all of the neurons have thresholds of 1. Now, this network calculates an XOR operation in the following way. At time step 0, we apply a spike if A is true or if B is true. We apply a spike to the appropriate neuron. And then 2 time steps later, the A XOR B neuron will fire if A XOR B equals 1. So meaning if A spiked and B didn't, or if B spiked and A didn't, then that one fires. Now, let me show you this in some animation form. Okay, so here I just have this network replicated 3 times, and I have 3 input scenarios. And I'll go ahead and animate this if I can. There we go. So concentrate, well, on the left scenario, there's no spiking. So the AX or B is never going to spike. In the middle scenario, B spikes and A doesn't. And so what you'll notice is those 2 hidden neurons, one of them gets a charge of 1, the right one, and one of them gets a charge of -1, which is the left one. The right one therefore spikes, and so it sends a spike to the output neuron, which also spikes. The neuron that had the -1 spike go into it leaks that charge away at the end of the time step so that it can start over again. And now if we focus on the right side where A equals 1 and B equals 1, and therefore A XOR B equals 0, both of them spike. And so what happens is both of them send a unit of, or 1 unit of charge to one neuron and a negative unit charge to the other neuron, and they all cancel out, and that's the reason why the output neuron doesn't spike. So this is the network that we're going to be exploring with our software tools so that you can get an idea of how they work. Okay, now what I've done is I've put up that network so that we can use it for reference with the node numbers right there. And what we're going to do is, here, let's move back to the main framework directory. And what we're going to do is that network is in kind of a deep nesting of directories. So we're going to copy it to this directory. So let's copy building blocks, RISP, XOR, star unform star temp.txt. There we go. Okay. Now, if we take a look at this network, this file, what you're going to see is it's JSON. If you're used to JSON, that's what JSON looks like, but it's unformatted JSON. So it's just a big old stream of characters, which is really hard to read. Now, you could use some JSON formatting tools if you want, but using the network tool is a much easier and effective way of reading through this JSON, taking a look at the network, and perhaps even doing stuff with it. Okay, so we have a program called the network tool. So if we say bin network tool, which we compiled earlier, it takes an optional command line argument, which is a prompt. I'll just give it a dash here, so we have a little dash as a prompt. And then if you type a question mark, it'll give you all of the commands that are part of the network tool. Too many to go over right now, so let's just go over some of the important ones. First, if we say, if we need to have a network loaded. If I try to ask for info, it looks like it just gives me an empty network. Okay, so if I want to read a network, I say FJ, which is from JSON. If I give it a file name here, it will read the file, which should be in the proper format, which it is. And now when I type info, it'll give me basic information on the network that matches the picture here, right? 5 nodes, 6 edges, 2 inputs, 1 output, and there are the identities of all the input, hidden, and output nodes. If I type nodes, it'll give me information on the nodes. You'll note it's formatted JSON, and edges gives me information on the edges. Now you'll notice that the IDs are not sorted, and that's because they are, stored internally as a hash table, which is not sorted. If you want to sort them, you can type the sort command. And now when we look at the nodes and the edges, you'll note that they're both sorted, which often makes it easier for you to find things. Now you can deduce by looking at this that the values in this array here correspond to the neuron thresholds. And then the edges have two values, and one of them will be a weight and one will be a delay. And you can again deduce that the weight's going to be the first one and the delay is going to be the second one. However, you can make this explicit, or it needs to be made explicit. The network stores something called a property pack, which you can look at with the P command. And this is in JSON as well. There are three sets of properties that your network has to define. So node properties are the values associated with each node and what they are. And so you'll note that's a threshold. Type to 68, that's a double. It's unfortunate that that's the ASCII value of the character D. And then here's the min and max values, goes between -1 and 1. The edge properties, you'll notice there are two properties, and we have delay and weight, and the index tells you where they are. So the delay is indeed the second one, and the weight is the first one. The weights are doubles between -1 and 1, and the delays are integers between 1 and 5. Networks can have properties as well, but this network doesn't have any, so none are defined. Okay. So now, if I type TJ, it'll convert whatever the network is internally into JSON. If I do it to the screen, it'll actually give me a nice readable JSON. If I do it to a file, it'll go back to being that unreadable JSON dump. And the things up top we've seen before. Here are the things we haven't seen. There are a specification of which neurons are the input neurons, which neurons are the output neurons. If there's any parameters associated with the network, that's where they would be. And then lastly, there's this thing called associated data. And what this tells us is what neuroprocessor runs this network, and more importantly, what parameters do I give the neuroprocessor when I instantiate it to create the proper neuroprocessor to run this network. So here it shows you that the name is RISP and that the parameters it takes is it needs leak mode to be enabled. That's because we want the neurons to leak their charge at every time step, even if they don't fire. Okay, now armed with this knowledge, we can use the network tool as a tool to give us information about single networks or collections of networks. If you're good at shell scripting, you can follow this. If not, you might want to skip ahead a minute or two. But what I'm going to do is I want to use the network tool to answer a question. For example, in a paper, I might have a collection of networks and I might want to say what's the average number of nodes or edges in that collection of networks. So let's do that. We've got a directory of networks here. That's back on our building blocks. So let's do GNP conversion. Okay, so this is a directory that has neural networks that do conversions between encodings. And if you look at it, there are 18 files in this. And let's say we wanted to calculate the average number of edges in these 18 network files. Okay, we do something like the following. So here, let's say for I in all these files, let's just echo I right in the shell script. Usually want to do it incrementally. Okay, good. Now what we'll do is for each one of these networks, let's go ahead and say echo FJ and FJ, the network name, and echo info, and pipe that into the network tool with no prompt. Okay, so what you see now is you've got that information. Each one of those calls is printing out the information for each one of those networks. Now, let's say we want to grep for edges, and actually let's go ahead and put that in a subshell so that we grep for the edges. That'll just be all done in one grep command. So here, grep edges. All right. And then from here, we can pipe that to awk, n plus equals 2, print, and over there are 18 files, right? Boom, we're done. If we really want to isolate it, like if we're going to do it in a graph there, tail-n1, and now we know that there's an average of 4.5 edges in those networks. Very useful to do things like shell script, to do shell scripting with this program. Okay, Now, let us suppose we want to modify the network. The network tool it gives you primitives to do that, and it's nice because that way when you're done, you can write out the JSON and everything will be done in the correct format. So let's go ahead and read that file again. So temp.txt, oops, bin network tool, fj temp.txt. Okay, that's our network again. Now, internally to the network tool, this is not part of the network class, but internally to the network tool is something called a name map. Okay? I'm not sure if I'm a huge fan of this, but this is how the student who wrote the network tool decided to do it. Right? Each node has a name associated with it, and by default, the name is just the node's number. But if I want to, I can add a new node to the graph, and in doing so, I need to give it a name. So that's the AN command. So if I say, let's just say I want to create a new node, I'm going to call it Fred. Okay? If I look at the nodes, you'll note that there actually is now a node 5. That's our new node. If we look at the name map, you'll see that Fred now corresponds to node 5. Now, it gives it a default value, which is going to be the max value for the property pack. But if I wanted to set the edge weight, I could set, for example, the neuron property, SNP. So I could say SNP Fred threshold 0.5. And now when I look at the nodes, you'll note that value has been set to 0.5. Now I can add an edge as well. So if I say add an edge from 0 to Fred, okay, now if I look at the edges, I'll see that there is a new edge from 0 to Fred, and its weight and delay have been set to their maximum values. And I could, for example, change that delay to 2 if I wanted by saying set edge property 0 to Fred, delay 2. And now I do that and you can see it's there. Okay, and then if I wanted to, I could write it to a file or I could write it to the screen. There's one more feature I want to show you, which is you can prune your network. And what pruning is going to do is pruning is going to do a graph analysis to discover all the nodes that are reachable from the input and that can reach the output. So basically every node where there is a path from an input to an output node and all edges like that. And so any node that's not on a path from an input to the output, and correspondingly any edge that's not on a path from an input to an output, will be discarded. Now you'll note that that this new node, Fred, is actually not on a path from an input to an output. It's just on a path from an input. So if I prune the graph, Fred should go away. So prune, and then nodes, you'll note Fred's gone, as is the edge. So it's a useful tool, especially when you're using, for example, machine learning tools to create graphs or to create neural networks. Pruning's a nice way of taking those and then reducing their size by eliminating stuff that's not necessary. One last feature that I want to highlight about the network tool is that you can randomize values of nodes and edges on a graph if you want. So for example, if you say RNP, let's see, 0, 1, 2, 3, and then you look at the nodes, you'll see that nodes 0, 1, 2, and 3 have been assigned random thresholds according to the min and max values that were in the property pack. Same thing with the edges. You can say randomize an edge property on the edge from 0 to 2, or randomize the edge properties on the edge from 1 to 3, but only do the delay. Okay, and then if we print edges, you'll see that indeed that was randomized, and we don't know whether that one was randomized or not. Let's try it again and see if it happens. Oh, here it is. I'm sorry, I was reading the wrong place, but yes, indeed it is. Well, it didn't happen previously, but it did happen on the second one. Okay, that's it for the network tool for now. Let's move on to the processor tool. So now you have to move into CPP apps. directory, and we're going to run the processor tool. Again, this is in the bin directory, and since you compiled it with the RISP processor, the executable name is going to have the RISP processor name on it. Again, you can give it a prompt. Again, question mark tells you all of your commands. Okay. Now the first thing we're going to do is I'm going to quit out of here. In the CPP apps directory, there is a subdirectory called params. This contains default parameters for all of our neuroprocessors and applications. So if you just want to create a neuroprocessor with default parameters, you can use these JSON files. Now that's important here. Let's run the processor tool again. And what we're going to do is we're going to make a processor. When we start off, there's no processor loaded in the tool. And so if we type make, we need to give it a processor name, which here is going to be RISP. And then the parameters file will be the file name of those parameters. So params risp.json. Okay, and it went ahead and created that processor. Now, once you've created a processor, before you've loaded a network on it, there are a few things you can do. You can get the name of the processor. You can get the JSON parameters that you can use to recreate the processor, which is a useful thing to have. And then if you say ppack, it'll tell you the property pack that needs to be put in networks that are going to be running this processor. Okay, let's make a new processor. Actually, let's quit. And let's go ahead and take a look at the network tool. And let's grab that previous file we had before. So fj, that's in our parent directory, temp.txt. Okay. Right. You'll notice here there are proc params. If I go ahead and use these parameters, this JSON here as the JSON to create my processor in the processor tool, then it will go ahead and create the processor that can run this network. So let's go ahead and do that. Okay, we'll say make RISP. And now if you want to enter JSON on the command line, you need to do it on the next line. So hit return, pop in that JSON, and there we go, name, params. You'll note it's not the same params that I used here, but it is parameters that we can use to create an identical instance of that neuroprocessor. Okay, now typically you don't actually go through those mechanics, but I just wanted to show you how they worked. Instead, if you have a network that's in the proper format and has this associated data, then you can use that network to go ahead and create the processor. So let's run the processor tool again. Okay. And if we say ml for make load, what that's going to do is that's going to take the name of a network. Here's temp.txt in the parent directory. And that goes ahead, grabs that associated data, and creates the proper instance of the processor. So if I say name, I've got it again. If I say params, all right, I have them, ppack will give me the property pack, etc. Yes, info, it'll give me info. It gives me some info about the network, not as much. This is just, but that's information about the network that has now been loaded onto this processor. Okay, once I have a network on a processor, I can apply spikes to its input nodes. Okay, so if we recall, here's the network that we're using. Let's go ahead and apply a spike to node A at time 0. You do that with the AS command. Okay, so that'll be node 0, spike time 0, and a value of 1. Okay. So that actually hasn't applied the spike yet, but it's queued it up so that when I run the processor, it's going to apply the spike. So let's just run that for, let's just say for 3 time steps. Okay. Now, when we've done that, it should be such that this neuron will go ahead and get charge and fire. This will get negative charge, which leaks away. And then this neuron will go ahead and fire, and it'll fire into the output neuron, which will then fire. So the output neuron should fire at time 2. Now we can, after we run, we can query the output neurons for what they've done. So if I say OC, that'll say what are the counts of the output neurons, and what we'll see is node 4 spiked once, which is what we anticipated. We can say OLF, and it'll tell us the time of the last neuron to fire, which was at time 2. And then we can say OV, that's actually going to give us all the firing times of that neuron, but it only fired once. So there's its firing time at time 2. Okay, and now we can, well, let's do a second example. We're going to have both A and B spike at the same time, time 0. When that happens, right, we're going to, each of the hidden neurons is going to get positive and negative charge and do nothing. So if I run 3 and then I ask for the count, it's going to say 0 because it didn't spike. These are all relative to the last run command. Okay, same thing. OLF will give me -1. OV will give me nothing because nothing happened. Okay, now I can queue things up to spike it multiple times with my AS command. So what I'm going to do is I am going to do 3 scenarios. So basically at time 0, so I'll just write it out. At time 0, I'm going to spike A. At time 3, I'm going to spike B. And at time 6, I'm going to spike A and B. Okay, and so what our expectations are here then is going to be at time 2, the output spikes, and at time 5 as well. Okay? That's what I'm expecting is going to happen, and then after time 5, we're going to get nothing because when at time 6, both of them spike, nothing's going to happen. Okay, so let's get rid of that. Instead, let's go ahead and add the commands to do that. So here we're going to have node 0 will spike it, or node A will spike at time 0. So that's going to be 0, 0, 1. Okay. Node B is going to spike at time 3. So that's going to be 1, 3, 1. And then at time 6, both of them are going to spike. So 0, 6, 1. And 1, 6, 1. Okay. Now, if you want to see what spikes have been applied, you can somehow, but to be honest with you, I don't remember the command, so I'm not going to show it to you. But if you hit the question mark, you'll be able to see which ones have been queued. Okay, I'm going to go ahead and run this for 10 time steps now. Okay. And so now when I look at the spike count, it should be that the output is spiked twice. Good. When I look at the last fire, it should be at time 5. Okay, and if I look at all the fires, we should have fires at 2 and 5. Perfect. Now you can also query neurons. Okay, if I say NC, that should tell me all the neurons that spike. Now I believe it takes a Boolean here. When you say true or false for whether or not you want to see things that don't fire, I'm just going to say true. Okay, so now what you'll see is, all right, we applied input twice to each of these neurons, so that's 2. Okay, we have the fire count being 2 here. Oh, that's right, this is 2 and that's 2. Each of the hidden neurons fired only once, and the output fired only once, or the output fired twice, once after the first application and once after the second application. So that's nice. You can look at their firing times. So NLFT, that shows you the time they last fired. And then if you want to look at all of the firing times, you can say NVT, and that will give you information on when everything fired. You can also get spike raster information. Same thing. By saying GSR, and that will actually give you a spike raster plot of all of the neurons, which could be useful in many different scenarios. Okay, I'm guessing that was a little bit of an abrupt cut. What I have here pictured on the left is a network that is slightly different from the one we've been working with. This one also computes a 1-bit exclusive OR operation, but this time it works on networks where there is no leak. The key is that -1 charge can't leak away when it arrives at node 3, and so we need to add some extra synapses so that when it does get set to -1, it gets reset. And that happens, you can see, for example, when node if you apply a spike into node A, then at the next time, node 2 will spike, node 3 will get a charge of -1, which it doesn't leak away. And then because node 2 spikes, at the next time steps, both node 3 and 4 are going to receive a unit of charge. The one at node 3 will cancel the -1. The one at node 4 will go ahead and spike the output. So it'll be all good. So what we're going to do is we're going to use this network to show how you can examine the current value of a neuron's charge when you're running the processor tool. So this network I have encoded in a file here. It's in my paste buffer, which is nice. Let's go ahead and run the processor tool. And we'll go ahead and run it with that. And now we'll do the ML command on that file. Okay. You'll note that that file specifies that leak is off. And so that's why in the parameter here, leak is off. Okay, so, and if we apply, let's just apply a unit of spike to node A and run it and make sure that it works properly. So if we say AS001, and then we go ahead and run for 3, we're going to see the output spikes. We can do a spike raster, GSR, true. And we'll see that indeed node 0 spiked, node 2 spiked, and node 4 spiked as anticipated. Now we can use the NCH command to look at the current charge value in all of the neurons. And they're all 0, and that's because node 3 received that -1 unit of charge, but then that was canceled by the 1 unit that came in from node 2. Now let's suppose we wanted to see that -1 unit of charge on node 3. We'll go ahead and add a spike with a value of 1, but now we'll just run it for 1 time step. Okay, if we look at the spike raster, GSRT, right, we'll see that indeed the input has spiked, and that went and that spiked into node 2, and now node 2 is spiked, but we haven't gotten to the point where that spike will be received. If we look at the charge values, you'll see node 3 has a charge of -1. And if we run for one more time step, right, GSRT, it'll only show the one time step, but indeed the output has spiked. And if we look at the charge, we'll see that node 3 now has 0 charge. Okay, now let's explore a little bit more. What we're going to do is we're going to put a ½ unit of charge into neuron A and 3/4 of a unit of charge into neuron B, meaning neither one of them is going to spike. So let's go ahead and do that. So we'll add a spike 0, 0, 0.5, and 1, 0, 0.75. And let's go ahead and run it for a while, 10 time steps. Okay. Nothing will have fired because the thresholds haven't met. So if I look at the spike raster, it'll show nothing because nothing has happened. If I look at the charge values, right, you'll notice that those charge values have been retained in the neurons because they don't leak. So if I go ahead and I add another unit of charge to node 0, so 0, 0, 0.5, and let's say I wait 3 time steps and I add 0.3, doesn't matter if it goes over, it'll still fire. So let's add, at time 3, let's add 0.3 to neuron B, which is neuron 1. Okay, here, let's run it for 10 again. Right. Now what you'll see is we look at the charge, they should all have 0 charge at this point. Right. If we look at the output, it spiked at times 2 and 5, right? Because that's when A fired and got propagated and B fired. And then if we look at the charge values, they should all equal 0 at this point. Yep. Okay, one last thing. Let's go ahead and let's add the same partial charges to nodes 0 and 1 as we did before. So, and then let's go ahead and run it for 4 time steps. Take a look. Okay, there they are. You can say clear A, and what that will do is that will run the processor's clear activity method. And what that does is that will zero out all of the charge values of all of the neurons, and it'll clear any spikes from the synapses. So I do that, and NCH, now you'll see they're all down to 0. So that's a nice thing. Okay, what we're going to do next is we are going to show how to hand construct a network for a specific processor. So let me get this picture here. What we want to do is we're going to use the discrete version of RISP. Let's cat params RISP discrete. There we go. Okay, with this version of RISP, the neuron charges and the synapse weights are integers instead of being floating point values. And you'll note we have the min and max weight values for the synapses are -10 and 10, so it's no longer 0 and 1. Okay, and then you can see there the threshold value, the delays are still 5, and there is no leak. Okay. Now what I want to do is I want to construct this specific network for this processor. And the way you do this is a two-part process. What you do is you're first going to create the processor. Okay, so we'll use the processor tool. And then we're going to make an instance of the processor. So RISP and this file. All right, we can verify params. All right, that's what it is. And you'll note the property pack now is different because, right, it has the synapse weights as here, the neuron thresholds is here, and you'll also note the types are 73, which is again an ASCII character code, but it means that they're integers instead of doubles. Okay, now there's a feature called empty net of the processor tool that if I call empty net, it will spit out the JSON of an empty network that has the proper property pack embedded and the proper associated data so that you can create the processor with it. So let's go ahead and give that a file name. So empty net, and let's call it simplenet.txt. Okay. So now I have this empty network. Now I can go ahead and use the network tool to add these two neurons and the single synapse. So let's do it. We can just run it from this directory, network tool. Oh, I forgot the prompt. All right, and now I'll say fj simplenet.txt. TJ, you can see it's the same network. And now what we're going to do is we're going to add two neurons, 0 and 1. So AN 0 and 1. We're going to have 0 be an input and 1 be an output. So AI 0, that says it's an input, AO 1, it's an output. Now I will set the thresholds. So SNP 0, threshold 9. And we'll set 1's threshold to 5. SNP1 threshold 5. So there they are. And then we'll create the edge. So add edge from 0 to 1. SEP 0, 1, delay 3. I think you can do it all on one line. Let's try it. Wait, 2. Oh, didn't work. 0, 1, delay 3, and SEP 0, 1, wait 2. There it is, and now I can set it. So let's say 2J simplenet.txt. All right, we can look at it. It looks fine. You'll note when we look at it, all right, it does have the inputs and the outputs set along with all of the edge IDs and parameters. Okay, now we're going to go back to the processor tool and run the processor on this network. And I'm doing this because there is some confusion that you might have when dealing with running the processor in terms of input values. So let's run the processor tool. And let's go ahead and make and load that network. Okay, we can see it created the right version of the processor. Okay, now let's go ahead and add a spike with a value of 0.5 to this. Now part of it is if we wanted to add a spike whose value was 5, it wouldn't let us do it. 0, 0, 5. it complains. And that's because the apply spike method only takes values between 0 and 1. If your processor accepts spike values that are not in that range, then it is up to your processor to convert these values into the proper values. The reason for this is we want uniformity among our applications. For example, if we have an application like the pole balancer, we don't want to have the pole balancer worrying about what the input range is. It always figures the input range is 0 to 1, and then it's going to be up to the neuroprocessor to convert that to whatever spike values make sense. So instead, let's go ahead and add a spike value of 0.5. Okay. And then let's go ahead and run it for one time step and take a look at the charge. All right. You'll note that because the maximum weight is 10, this version of RISP scales by a factor of 10. So 0.5 corresponds to 0.5 times 10, which equals 5. So the neuron is holding 5 units of charge. If I go ahead and put in another half a unit of charge, 0.5, now the neuron will spike. If I say run 1, the neuron should have spiked. Yep, it spiked it at time 0. If I look at the charge values, they're all 0. Why? Well, this synapse has a delay of 3, and so since it spiked at time 1, now the spike is traveling along the synapse. If I run for a few more time steps, so here let's run for another 5 time steps, and then I look at the charge, now I should see that neuron 1 is sitting there with a charge of 2 because of its incoming synapse with a weight of 2. There it is. And if I apply, let's just say I apply 2 more spikes with values of 0.9. So here, let's do that into node 0. So 0, 0, 0.9, and 0, 1, 0.9. So 2 successive spikes of values of 9. So that neuron will spike, and then 3 time units later, you'll get 2 successive spikes whose weight are 2, so the output neuron should fire. So let's run. We'll run it for 5. Okay. We'll see the output did spike. Spiked at time 4. Look, we look at the spike raster. Okay. That's there. And if we look at the charge, we should have no charge. And that's because after spiking, everything got reset. Okay, so given that, if you want, you can write programs or shell scripts if you want to do certain kinds of neuronal activity to do your own testing. So we're going to do that with one final example using this network. What I'm going to do is I am going to spike in a value of 0.5, 12 successive time steps into this input neuron. That will result in spikes whose values are 5 being spiked into the neuron, and that means that every other time step it'll fire. Now, when it fires 3 time steps later, this spike goes along this synapse and reaches this neuron. It will add 2 to its charge, so that every 3 spikes of neuron 0 is going to result in 1 spike of neuron 1. Okay, so that means after every 6 time steps on neuron 0, that will result in 3 spikes going into neuron 1, which will be 1 spiking of neuron 1. So if I put 12 successive spikes into neuron 0 and then run it, I will expect to see neuron 1 fire twice. So let's go ahead and do that. And again, we can do this with awk if we want. We can just do it in the shell if we want. Now let's do it with awk. So let's go ahead and generate those AS commands. So we'll say echo that into awk. For I equals 0, I is less than 12, I plus print 0, the delay is I, and 0.5. Oh, and let's print the AS. Okay, well, let's just take a look at that. Okay. Oh, not $, my bad. Not that either. Need a comma. Okay. There we go. Okay, so let's go ahead and do the following. We will do the proper ML command. So let's echo ML simple net.text. Then we're going to go ahead and do this command. And then we're going to go ahead and run it. Let's just run it for 20 time steps. And then let's take a look at the spike raster. Pipe that into processor tool. Oh man. Oh, I didn't do echoes. So echo and echo. Boom. So what you see is indeed we got 6 spikes every other time step, and then after that set of 3 spikes, we accumulated enough for the output to spike and accumulated enough for the output to spike. Now I will say the framework has all of this functionality built in so that you can use methods and objects in C++ to accomplish all of this. But the processor tool and the network tool are 2 nice command line tools that give you a lot of ways of exploring that functionality, and so they make life easier for you when you're exploring how these neuroprocessors work. That concludes this walkthrough. I hope it has been useful for you. If you see any problems or if you have any questions, please don't hesitate to contact me. Thank you.